This session we get into the nitty-gritty, the detailed math of the STED, S-T-D-E, time-dependent equation of Schrödinger. So remember the Hamiltonian in the Schrödinger equation we split into two parts, H0, which we assumed was time independent, and it had energy eigenfunctions un, and the second part of the Hamiltonian was H dashed, which was assumed to be time dependent. Right? So here's your time dependent part of the Hamiltonian. Okay, so plug in the value. In the previous session we assumed that the Schrödinger wave function psi is now a function of r and t, time, and it was equal to the sum of a n, the coefficients, the weighting coefficients, which are now a function of time, so a n of t, un only of r, and the exponential term e to the, what is it? E to the minus I e n t over h bar. Yeah, right? So plug that psi function into the STED, the Schrödinger time dependent equation, and I ask you to do it for homework. Yeah, it's pretty easy, right? So the left hand side, that's the h. This is your h, right? Your Hamiltonian, the total Hamiltonian, the basic Hamiltonian plus the perturbing, or the unperturbed plus the perturbing Hamiltonian. So you got your h, and the rest is basically psi on the left side, and on the right side that's equivalent to your I h bar d psi by dt. Okay? Now if you're plugging in the psi, the weighted sum expression for psi, you'll get this. Right? Now here, remember your I, your A's now depend on time. So you will be differentiating those A's. Okay, so that's where this A dot, you see this dot here, that means you have differentiated the A with respect to time, d by dt. Okay, so get that expression, do that as homework, pretty easy, not too difficult. Alright, now we can simplify things a bit. Notice that h naught un is the same thing as en un. Why is that? Well, from here, right? Because it's the eigen equation for stationary states, the unperturbed, the time independent part of the Hamiltonian. So you've got h naught un is en un from the eigen equation. So this and this, those two terms drop out because they're equal. Okay? So kill those. So you're just left with the h dash term. That the h0 is gone. This is gone. So you're left with this. All right. Now multiply. That's what this big X means. So multiply on the left of both sides by um star. The conjugate of um, right? So you've got n's here, here's an m. So multiply both sides on the left by u star, or um starred, the conjugate, I becomes minus I. And then integrate. Now it depends on, are you talking a one-dimensional system or three-dimensional system? If it's one-dimensional, integrate with respect to x, dx, integral dx. If it's a three-dimensional system, then you integrate with respect to volume, dv, d tau, whatever. Okay, so do that, and so you multiply by u, you integrate, and you'll get this. So do that also for homework. Okay, now can you see where, now this is gone, right? That's gone. So you'll get sigma an, that's where this is, integral um star h dashed, right? Un Now this doesn't depend on the volume or the x. Let's see, you can take that outside the integral. So that's your new left-hand side. And now that term is gone. So you got IH sigma A dot, okay? And integral U star M U N dt. And look, I've run. I'm anticipating, I've said this several times, but up until now, I've been able to put equations pretty much into a single square. You know, the width of the square was enough to put equations, but I ran out. Look, I mean, I could have squashed it up a bit more if I knew, but so you know, this exponential term gets tucked here on the right. So, you know, as I get to higher levels, I see it's inevitable, given the length of the equation, especially in quantum field theory and such like. So, expect in the future I will just be using two squares, and I'll just be writing like in a long sentences, especially long equations, across two squares, as treated as a unit, as a rectangle, a single rectangle. That's coming. All right. Now, okay. So do this. You know, derive this equation for homework. Again, not too difficult. You can almost do it visually by inspection. Okay. So a couple of remarks now. You're just looking at this equation. Have a look at this. You've seen this kind of thing before. It's the perturbation matrix, right? H dashed, UM in front, UM behind. So this term here is the mnth element of a matrix, the perturbation matrix. So the nth element, you know, the nth row, the nth column of this H bar matrix. So that element, you know, just one element of the let's say m and little n range over big N elements, then that matrix would have size n, big N squared elements in the matrix, right? And that's just one of them, one element of big N squared, and it's this term here, right? So you can rewrite that as just H dash mn, okay, for here. Now the right hand side, this term here, well, that's just the orthonormality integral, right? If m equals n, that integral will just be 1. And if m and n are different, that integral will be 0. It's the delta function. It's the delta function integral, if you like. Right? So you can rewrite this as just delta mn. Okay? So this integral here is just delta mn. Alright, so let's say m equals n. So you just get a single 1 here, and all the other terms go 0, drop out. So your sigma will disappear, and you'll just be left with an am. Okay? So that's where this comes from. So this a dot here, and there's just one of them. All the others 0. So you've got that here, and this IH bar you take over the other side underneath, and it's 1 over. Okay. Sigma, and this you rewrite as this. Okay, so there it is here. That's just this, and then an here, e to the I. Now this is a bit different. I've got this omega mn. Where'd that come from? Well, you've got this term and this term. Okay, so take this over, and so. Now this will become em, yeah, because of this delta function here. It's become em, and it'll be plus. So this omega here is the difference in these energies. So em minus, you can minus here, minus en, and divide by h bar. So it's you've created a new term. You're talking about this omega mn, which is defined, you know, 3 bars as the difference in the energies. Divided by h bar. Okay, so yeah, it's just just plugging things in and cancelling out a bit, that shouldn't be too difficult for you, so long as you've understood the theory so far, right? Perturbation matrix, delta functions. This is all theory from earlier chapters, right? So this is pretty well exact. Okay? Right, now I will turn the chair around. This afternoon, during the daylight, I'm doing this at night now, I was busy assembling a new dining table set. So with a new nice high quality nice wooden dining room table and 4 chairs, and I'm now sitting on one of the new chairs. So as I turn myself around, I'll let you see the chair. So okay, for the second half of this session, right? Now that equation we got for A dot M, so it's an expression that gives you the rate of change with respect to time. So d by dt of A M. So it's the mth coefficient in your psi. Psi being a function of r and t. Okay. So we have an expression now for A dot or AM dot, the differential with respect to time, d by dt of AM. And it was 1 over IH bar sigma n h dashed mn an e to the I omega mn t. And I don't know if you can see it here, but so I'll use that later in later sections. So I've identified this equation here for AM dot with a plus circle.